Hey, what's up, guys? How you guys doing? Good to see you. Well, I hope you guys are having an amazing day. Welcome back to Two Men, One Course podcast. My name is Pete. I'm your host. Tyler will show up in just a little bit, so hang in there. All right. So, same drill. To start out of the podcast, let's talk about joke of the day. You guys ready? Yeah. All right. First one. Why do pancakes always win at baseball? Well, because they have the best batter. one more. What do sprinters eat before a race? Nothing. That's why they're fast, man. All right, so now next one. So we have a limiting reagent this lab. Okay, I'm sure you have learned this in lecture before, but let's review about it real quick. Okay, so take a look right here. So if I want to make a carbon dioxide gas, so of course, like in the balance equation, I'm going to need a 1 mole of carbon and 1 mole of oxygen gas, or two atoms of oxygen gas, same thing. Okay. All right. So how many molecules of carbon dioxide I can make if I have this number, this atom of carbon, these molecules of oxygen? Pause the video and let me know. Well. So let's say what we got. We got 12 atoms of carbon and 9 molecules of oxygen. Okay. So these are the simple molecules, of course. You guys can do that. Now, I'm sure you know how to do this. But let's go back to the basic. Just to review. If I look at just the amount of carbons, so 12 molecules of carbon, I supposed to get 12 molecules of carbon dioxide. Does it make sense? Right? Just look at the carbon, not the oxygen, just the carbon. If I have 12 atoms of carbon, I should be able to make up to 12 molecules of carbon dioxide. But now, if you look at the numbers of oxygen molecules, okay, 9 molecules of oxygen gas, I suppose to get 9 molecules of carbon dioxide. This number 12 and 9 molecules of carbon dioxide are theoretical yields. Okay, in theory, this is what you get. You have in theory, if you have 12 atoms of carbon, in theory, you should get 12 molecules of carbon dioxide. If you have 9 molecules of oxygen gas, in theory, you should get 9 molecules of carbon dioxide. That's what I mean. But how many molecules of carbon dioxide I supposed to get in this case? Well, it's one carbon per one oxygen gas, right? So one, so that's how many? 2, 3, 4, 5, 6, 7, 8, 9. That's it. Once one of the reactant gets used up, the reaction stop and just stop right there. So are we getting the total of 9 molecules of carbon dioxide? Okay, so who's the limiting reagent? Limit the number of carbon dioxide? The oxygen gas. Okay, and the real theoretical yield is the 9 molecules, not 12. All right, so just a review. So the limiting reagent, the reagent that is consumed completely, the limiting reagent determines the amount of product determine the amount of carbon dioxide. Okay, in this case, and theoretical yield is the maximum amount of product that can form, or 100% yield. Sometimes we call that. All right. Okay, let's say if I have this equation, let's use to a real chemical equation. Okay, so I'm having using sulfur trioxide react with water to make a sulfuric acid. Okay, so let's say we got 20 grams of sulfur trioxide, 10 grams of water. So what is the theoretical yield of this reaction? Okay, so we get a little bit problem here. So 20 grams and 10 grams. Gram is nothing like mole, right? If you look at the equation, this is the balance equation. The balance equation says that we're going to need 1 mole of sulfur trioxide and react completely with 1 mole of water. Okay, it's 1-to-1 ratio. And mole is not grams at all. Totally not. Okay, well, we have 20 grams of sulfur trioxide and 10 grams of water. What are we going to do? Well, make it the same unit here. Okay, so we can convert grams to mole using molecular weight. I'm sure you can do that, right? Convert grams of sulfur trioxide and water to moles, and look at the moles right here. You can tell that we have way too many water, right? Way too many water. We have little, only half of sulfur trioxide in moles. You know that? Now, so who's limiting reagent, who's left over, who's excess? Let's take a look right here. Well, sulfur trioxide has less mole, so use them all up. Okay, and since sulfur trioxide and water react 1-to-1 ratio, if you use this mole of sulfur trioxide, we'll use the same mole of water, same number there. All right, and also 1 mole of sulfuric acid, so same mole with sulfuric acid. Okay, so I set up like this so you guys can see it very clearly. At the end, so this we're starting with the initial, right? Delta when change when they do reaction, and at the end, final. That's at the end. Well, we used up all sulfur trioxide, so you get 0 left. Okay, water, we use this amount of water, so we're going to have this left of water. All right. And last one, so we're making 0.2498 moles of sulfuric acid. Start out, we don't have it, right? And we make this amount during the reaction. At the end, we have that amount, basically. So now you can see that the excess reagent is water, and the theoretical yield is right there in moles. Who's the limiting reagent? Sulfur trioxide, limit number of sulfuric acid form. Okay, so I'll give you an analogy right here. So if you have like more mass, so if you look right here, you have a lot of sulfur trioxide in gram, right? We have only 10 gram, only half of sulfur trioxide, but gram is doesn't really tell you anything actually in terms of stoichiometry. All right, give you some example. If you have a 200 pounds of a 50 pounds dumbbell, how many dumbbells do you have? Only 4, right? Only 4. That big number here doesn't tell you have a lot of it, right? Compared to if you have 100 pounds of apple, and each apple weigh only 0.2 pounds. Well, if you do the math right here, you have about 500 apples. You have a lot more apples, like in terms of number of apples, right? If I'm going to arrange a basket that contains 1 dumbbell and 1 apple, who's limiting reagent, who's limiting object? The dumbbell. The more mass doesn't mean you have a lot of it, right? You have to convert, you have to look in moles. Okay, all right, go back right here real quick. So right now, so we have theoretical yield in moles of sulfuric acid. If I ask you in grams, you should be able to do so. So convert moles to grams. So using molecular weight, 1 mole of sulfuric acid is 98.08 grams of sulfuric acid. Do the math right there. You should get that number, and 466 round down. Ta-da, 24.50. Okay. All right, I'll have you try on your own right here. So pause the video and then now check with me. All right. So how much glycerin, so C2H5NO2, this guy right here is a product, could be expected in grams. So expected as this. That's a theoretical yield. That's another way to say it. All right. From reaction between carbon dioxide and ammonia using this amount. Okay. All right, now, first off, you make sure you check the equation. If you balance the equation first, always balance the equation. This one has already been balanced, so you'll be good. Okay. All right. First off, so well, we have 2 reagents, right? So we assume that methane CH4 is excess. Okay. So right now we just look at either carbon dioxide and ammonia. These 2. Okay. So one of them gonna be a limiting reagent, limit the amount of glycerin formed. Okay, so you need to be able to find the limiting reagent first. All right, so let's do it together here. So we have 29.3 grams of carbon dioxide, 4.53 grams of ammonia. Well, grams, it doesn't really tell you how much you actually have. So convert it to moles, right? Using molar mass, convert all of them to mole. Now you can see exactly we have so little amount of ammonia, but we have much more for carbon dioxide. That. Okay. All right. From right here. All right. That's what we're starting with. So we don't have any glycerin. When you do the reaction, we use all up ammonia, 0.2658 moles. Okay. How much carbon dioxide do we use? Well, it's going to be double because watch out here. It's 1-to-2 ratio, 1-to-2 ratio right here. Okay. So we're going to double the amount of carbon dioxide. All right, and the same thing with glycerin. So it's 1-to-1 ratio with ammonia. So use this amount of ammonia, you will make the same amount of glycerin. Okay, so watch out just the coefficient in a balanced equation. All right, now at the end, the amount of reactant should be lower. So minus subtract right there. So you should get that amount of carbon dioxide left. No more ammonia left. We use them all up. Okay, and the glycerin, just that. All right, so who's the limiting reagent? The ammonia. don't have a lot of it, right? The excess, the carbon dioxide excess, and the theoretical yield is that number. Okay. Now the question asks, so how many grams of glycerin do we get? Well, we take we have moles convert to gram. Super simple there. Use molar mass, right? So 1 mole of glycerin is 75.08 grams of glycerin. Do the math right there. You should get that number. 3 6 write them up. 20 grams. Okay, this is the one way you can do this. You can set up the table, initial, delta, and final. Okay, you can do this too. Or some of you might, depends on the instructor in Gen Chem. Okay, so my instructor teach me like this. So this is another way to do it. Let's take a look. All right, I'm going to, hold on. Okay. All right, I'm going to use grams of carbon dioxide and grams of ammonia. Convert grams of these two to the grams of glycerin right away. Okay, and to do that, so start with ammonia. So I'm going to convert it to mole first, and mole of ammonia to mole of glycerin, and from mole of glycerin to grams of glycerin. Go in that route. All right. So we want a grams of glycerin right here, starting with 4.53 grams of ammonia. Grams to mole using molar mass. That gram cancel with grams. Now we have moles of ammonia now. From mole of ammonia, convert to mole of glycerin. 1 mole of ammonia is 1-to-1 ratio. 1 mole of glycerin is 1-to-1 ratio. Look at the coefficient in the balance equation. All right. And the last step, convert mole of glycerin to grams of glycerin using molar mass. So 1 mole at the bottom and 75.08 grams of glycerin at the top. Do the math right there. You should get that number. 20 grams. Okay. All right, so look at ammonia, just ammonia. You should get 20 grams of glycerin. Now we're going to try carbon dioxide. Okay, 29.3 grams. So same thing, same drill. Grams to mole of carbon dioxide, and mole of carbon dioxide to mole of glycerin, and mole of glycerin to grams of glycerin. Just same pattern there. Okay. All right, so we want grams of glycerin. So right now we start with 29.3 grams of carbon dioxide. Convert grams to mole using molar mass. All right. All right, we're going to we get moles of carbon dioxide now. From mole to carbon dioxide to mole of glycerin is 2-to-1 ratio. See that? It's 2-to-1 ratio. So put 2 moles of carbon dioxide at the bottom, 1 mole of glycerin at the top. So mole cancel with mole. Lastly, so mole of glycerin to grams of glycerin using molar mass. You should get this number. Okay, the rest is going to be sig figs or 3 sig figs. Write them up. Yeah, totally. Limiting reagent is ammonia because it produces less amount of glycerin. Stop right there. Can't go over 20 grams. Right? And that is the theoretical yield. All right. All right, so that's the limiting reagent. So go a little bit further. Okay, so I have a little bit story to tell you. All right, so some of you know that I graduated from graduate school from University of Missouri. That's the column, which is the iconic scene, architecture of the University of Missouri. Okay, I got a PhD, got my degree in that building. All right. Anyway, so this is a little bit about my PhD research. So I do something about the DNA, just small amount of my PhD research. Okay, so just a little bit about DNA. So I'm sure many of you know that a DNA consists of 2 strands of deoxyribose. There's a deoxyribose strand. 2 strands stick together. All right, and they are stick together because there are interactions between 2 nucleobases. You probably have heard AT and C and G. Okay, all right. Now I'm sure you know all of this. Now we're going to talk about the sugar, the ribose right here. So this is a ribose molecule. Look like this. Now you probably have seen this before. Not a glucose though, right? Glucose is a 6-membered ring, and ribose is a 5-membered ring. But the ribose in DNA is a deoxyribose, not just a regular ribose, right? It's right here. So it's 2' deoxyribose, which means deoxy means remove the oxygen at position 2. So this is position 1, this is position 2. So remove the OH group right here, 1 oxygen. Okay, so basically that's it. 2 deoxyribose. I was an organic synthesis. I was doing the organic synthesis in the graduate school, and one of the many reactions that I do just to put a benzyl bromide, look like this. You will learn this much more in our organic chemistry. Okay, attach benzyl bromide onto deoxyribose. All right, so I'm going to add some amount of deoxyribose, some amount of benzylbromide. One of them going to be limiting reagent, which is actually the deoxyribose. We have a lot of benzylbromide. It's cheap. We add a lot of it. All right, adding a base, sodium hydride at the top. This is a base. THF is a solvent, and RT. You want to guess what RT mean? It means room temperature. So just a regular temperature. It doesn't have to heat it up or cool it down. Okay, I want the expected product looks like this. Okay, now from my calculation, the theoretical yield is 15.3 grams. Whatever how much I start of deoxyribose I start with, I should get the product about 15.3 grams. That's the expected product amount of product. Okay, now in reality, that's what I got. 0.21 gram. That's an actual yield. In theory, I should get 15.3. Right now, I got only 0.21 grams. That's low. That's really, really low, right? Well, I have to talk to my advisor. Okay, sir, it doesn't work. So this reaction doesn't work. I have to report him as a percent yield. And percent yield can be calculated as the actual yield over theoretical yield times 100. All right, pause the video right here. Use this number, calculate the percent yield for me, will you? All right, pause the video right here. Okay. All right, so 0.21 grams divided by 15.3 times 100. That's the percent yield. Only 1%. Oh my God, this reaction sucks, man. That doesn't work. Well, as a chemist, so we have to find a way to make this work. All right. So run another reaction. Right. This time I'm adding a catalyst. I mean, the active is an activator, so should make this reaction better, right? Give me more yield. Look what I got. Same thing. So 0.21, 0.2 gram is same thing right there. Doesn't work. Well, try heat it up, right? Now I got 0.3. That doesn't work. Nothing changed, right? I supposed to get 15.3. Right now I got like 0.3 gram, 0.2 gram. What the heck? So, well, change the solvent. Maybe solvent doesn't do good. DMF, there's another solvent you learn in organic chemistry, right? And I got 0.18 gram. Well, nothing's working here. What's going on? Keep in mind, its reaction take about 3 hours, right? And after the reaction, you have to go through all the separation technique to separate the product from the leftover starting material, from the solvent, and from the whatever reagent you add into it. That's take about 5 to 6 more hours, right? That's one reaction. And I've done a tons of reaction just to make this reaction work, right? Well, a few weeks later, I just keep trying and trying and trying, but it doesn't work, right? So it's been week and a half so far. Nothing's working. Talk to my advisor. He said, I don't know, man. I never done this reaction. You could try to do something to make it work. So, well, it's probably something that's going on in here. So I went and checked the bottle of benzylbromide because it's a very old bottle. It's been there forever, right? Check the structure. Kind of sketchy. So I ordered a new bottle of benzylbromide. Ordered a new bottle, brand new. Okay. Now check the structure of the starting material. Deoxyribose is 98% pure. So nothing wrong with it, right? And then do this reaction with the new bottle of benzylbromide. I still get 0.2 grams. Like what the hell? It's been almost 2 weeks. Nothing happened. It's just an easy reaction. Well, I add the activator, the catalyst, change the solvent, change the temperature, check the structure of benzylbromide, check the structure of deoxyribose. Nothing works. Anyone here knows? There's one more thing, one last thing. I haven't checked it yet. This guy right here, sodium hydride. It's a base in this case. I never checked it before. I look up the literature and realize that, sodium hydride actually, it can react with the moisture in the air. That's water, moisture in the air, and turn to be sodium hydroxide and hydrogen gas. And sodium hydroxide is not like sodium hydride at all. Much less basic than sodium hydride. Okay? So this is what I did. Take sodium hydride that we have. It's an old bottle as well, right? Put into the Billner funnel. This is a Billner funnel. You will do this in the lab, okay? Put sodium hydride right here and then wash it with the organic solvent, right? Make sure it's clean, no sodium hydroxide or anything else on it. So use pure sodium hydride, right? Now, once I've done that, do the same reaction. Take a look at the yield. 14.1 grams. Look at that. Oh my God. Now, pause the video, calculate the percent yield from here, would you? 14.1 grams. What's the percent yield? All right, so 14.1 grams divided by 15.3, that's a theoretical yield times 100. 92% yield. Look at that. 2 weeks later, finally, one reaction. It works. Well, I mean, I was crying, right? Oh my God, finally. All right, so just to remind you, the theoretical yield is the maximum percent yield or 100% yield, basically. All right, the actual yield is what you actually get, right? It doesn't have to be. It's always it's never you never get 100% yield. You probably lost in while you transfer from one container to another to a separation technique. I mean, you lose some anyway. The the highest yield that usually people usually get is like 97-98% yield. That's like the maximum that I have seen. Okay. All right, now let's say what is percent yield of glycerin? So the theoretical yield is 19.96 and the actual yield is 15 grams. Okay, so what's the percent yield? Well, that's a formula. So 15 divided by 19.96 times 100, you should get that right there. Okay. All right. I hope this helped you catch up with or learn about the theory behind the lab. All right. So let's take a look at the next podcast with you.